Hello and welcome. The other day my friend told me to stop impersonating a flamingo. I just had to put my foot down. In this video, we're going to look at finding the absolute max and absolute min values of a function. Let's get started. Suppose we have a function with f with domain D. Then f has an absolute maximum value at a point C in the domain if the function value at C is bigger than or equal to all other function values. So in the case of a local maximum, all we needed to be was the biggest function value nearby, but to be an absolute maximum, we need to be the biggest function value of all, bigger than or equal to at least. For the absolute minimum, the reverse has to happen. We have to be the smallest function value out of all of the function values in the entire domain. Looking over at the graph on the right, what is the absolute maximum value that you see? If you said 4, then that's correct. The absolute maximum value that you see is 4. There's the absolute max. It happens at x equals 2, but the absolute maximum value of the function is 4. It's like the highest peak, right? Is 4 feet off the ground. Not a very high peak. 4 miles, there we go. What about the absolute minimum value of this function? If you said 1, that's correct. One is the absolute minimum value of the function. So sometimes the absolute max or absolute min could happen at a peak or possibly a valley. Or sometimes notice it could happen at the endpoints, right? This was a max, it was a local max on the right side here at x equals 5, but not the absolute maximum value. This was a min, and it happened to also be the absolute min of 1. Absolute maxes and absolute mins are also called global maxes and mins, or absolute extrema when you combine them together, or global extrema. All of these are talking about the same thing. In example 1, we're asked what are the absolute max and absolute min, if any, of y equals x squared, given some different domain considerations. So here's the graph with the domain negative infinity to infinity. What would be the absolute max, if any? If you said none, that's correct. There isn't an absolute maximum value. The y values just keep going up to positive infinity and they don't have a ceiling. What about the absolute minimum? That would be 0, and it happens at x equals 0, just to give a little bit more information. That's right there at the bottom of the parabola. Let's look at the domain of 0 to 2, including 0 and including 2. What's the absolute max value there? If you said 2, which happens at x equals 2, if you said 4, which happens at x equals 2, then that's correct. The highest y value that we see is 4, and it happens at x equals 2. What about the absolute min? If you said 0, that's correct. Sure of it this time. And it happens at x equals 0. That's the old absolute min that we saw with the other domain. Now we're changing the domain to 0 to 2, not including 0, but including x equals 2. What's the absolute max here? If you said 4, then that's correct. And the absolute min? If you said none, that would be correct. There would be an absolute minimum value of 0, but it's not there. And there isn't any other absolute minimum value because as soon as you say, let's say the absolute minimum value is 0.1, let's just say, well, there's always going to be a number smaller than that. 0.05 would be smaller than that. And then if you set it at 0.05, you could just do 0.005. And if you do 0.005, you could do 0.0005. There's always going to be a number that's smaller than any number that you give. So there isn't any single absolute minimum to this graph with this domain. What about if you took out both the endpoints? So 0 to 2, but not including 0 and not including 2. What would be the absolute max? We said none, that's correct. And the absolute min? Also none. Because those two, absolute max and absolute min, that we used to have are now being plucked out of the graph. So when are we guaranteed to have an absolute max and min? We saw in those examples, if we restrict the domain in certain ways, we don't get an absolute max or an absolute min. This is where the extreme value theorem comes in. It says that if f is continuous on a closed interval from a to b, so including those endpoints, then it's guaranteed to have an absolute max and an absolute min on that interval somewhere. Let's look at these examples. So here we have a closed interval from 1 to 4. The absolute max is happening at this endpoint right here. So the absolute max is 3. And the absolute min is happening at the other endpoint. Let's just draw little dots for the absolute max and absolute min. There's the max, there's the min. The next graph also is a graph from the closed interval from 1 to 4, including the endpoints. Here, what's the absolute max? We said 3, that's right. And the absolute min? 0. It's happening at x equals 3, but the minimum value, absolute minimum value, is 0. So it looks like sometimes the absolute max and absolute min can happen at endpoints, or it could happen in between the interval at maybe a local min or possibly a local max, like in the next example. So here, the absolute max is happening at a local max, right there at x equals 2, but the absolute max itself is 4. What about the absolute min? If you said 1, that would be correct. And for the last example, absolute max is 3, and the absolute min is 1. Now here we had some local mins and local maxes, but they weren't big enough to be the absolute min or the absolute max. Now the extreme value theorem, if you think about it in general, if you take any 2 points, the starting point and the ending point of your interval from a to b, so take, this is like at x equals a and x equals b. And if the graph is continuous, if the function is continuous, then you can't pick up your pencil to go from this point at a to this point at b. So if you can't pick up your pencil, then either the graph is going to go from point A to point B, and you'll have the local min at the smaller point and the local max at the bigger point, or the graph will go above the point at B, and then it'll have to come back down to get to B, right, because you can't pick up your pencil, in which case you're going to have a max somewhere in between, or it's going to go down below the minimum value at A, and then create a new minimum value and then come back up to B, or it may actually go down to give you a new absolute min and then go up to give you a new absolute max before coming back to the point at B. So, but there's no way really around having an absolute max or an absolute min. It's either going to be at the endpoints or at some local max or some local min in between. Now, if you don't satisfy the conditions, like let's say the function is not continuous, then you're not guaranteed to have an absolute max or an absolute min. And here's an example of that. Here's a function that's defined on the closed interval from 0 to 1. It's got a y value for each of those x values from 0 to 1, including the endpoints. But the function is discontinuous. You can see right there at x equals 1, the function is discontinuous. And so we can see that the extreme value theorem doesn't apply for one thing, and this is an example where we don't have an absolute max, right? Here the graph goes up. There would be an absolute max there of 1, but that point is removed and instead is down here. So we don't actually have a max there at 1. But if the graph were continuous, that kind of thing couldn't happen. and so you'd be guaranteed to have an absolute max or an absolute min. In the next video, we're going to find the absolute max and absolute min given an algebraic form of a function. Thanks for watching, and see you in the next video.